In this video, we're going to introduce another flavor of strong induction. So remember, we use strong induction when we want to do an induction style proof, and so we make some assumption, and we want to prove that P of k plus 1 is true in the inductive step. But whereas in standard or weak induction, we know that just assuming P of k is our starting assumption, the inductive hypothesis for proving that P of k plus 1 is true, we may, in strong induction, need to look farther back to P of k minus 1, P of k minus 2, and so on. And so this motivates us to look at strong induction. Last time we looked at bounded strong induction. So in bounded strong induction, we know how many steps back we're going to need to look. And so we look back that many steps and prove that many base cases. Today, I want to talk about unbounded strong induction. So in unbounded strong induction, what we do is we say, hey, for all choices of j, which are greater than or equal to n naught and less than or equal to k, P of j is true. That's my inductive hypothesis. This is telling me, hey, I'm going to assume P of j for everything up to and including k. And I'm going to use that in the inductive step to demonstrate that P of k plus 1 is true. So my inductive step says, hey, assume that P is true of every j up to and including k, and that's going to get me to k plus 1. So a funny thing about this approach is that even though I'm assuming an unbounded number of propositions here, so k could be really big, in which case, if k is really big, then I'm making a lot of assumptions here. K could be 1,000, in which case I'm making 1,000 assumptions of the form P of j. But surprisingly, and we'll see an example soon, unbounded strong induction usually, not always, but usually requires only one base case. So we do a standard type base case where we prove the statement is true for n naught, and then we need to use unbounded strong induction in the inductive step. Our inductive hypothesis, we assume this very large, potentially, number of propositions, and we again use it to show that P of k plus 1 is true. So let's do an example. In this video, we are going to use strong induction in its unbounded form to prove a version of the prime factorization theorem. So here is a reminder. A natural number, n, is called composite if it has a divisor other than 1 or n itself. And a number which is not composite is called prime. So when you think about, okay, what numbers can I create by multiplying other numbers together? 6 is a composite number because I can create it by multiplying two numbers together, 2 and 3, neither of which are 1 or 6. So that's a proof that 6 is composite. Very good. Okay, so here's the theorem. This is a part of the prime factorization theorem. The theorem that we're going to consider here is that every composite number can be factored into primes. So for example, 120 is a composite number, and I can factor it all the way down into its prime factors. That's 2, 2, 2, so 3 copies of 2, of 3, and of 5. It's also true that, in fact, this factorization is unique up to order, but we won't prove that here. So if I wanted to prove this fact that every composite number can be factored into primes, I could use unbounded strong induction. So let's go ahead and do that proof. So as I mentioned, our base case in unbounded strong induction is often relatively simple. I just need a single base case. So let's try to do this really quickly. The smallest composite number that should be our base case. What's the smallest composite number? Well, 1 is prime, 2 is prime, 3 is prime, and so the smallest composite number is 4, which can be written as 2 times 2. That's our factorization. We have factored the number 4 into primes. Check, our base case is established. Okay, so now on to the inductive step. And this is where things feel a little different from the standard or weak induction technique that we've learned before. So I'm going to assume for all n less than or equal to k that if n is composite, then n is factorizable into primes. So that's my inductive hypothesis. We'll show that if k plus 1 is composite, then it is also factorizable. Okay, how are we going to show this? So let's go ahead and suppose that k plus 1 is composite. I'm making this assumption for free because if k plus 1 is not composite, it must be prime, and my theorem is only about composite numbers. I don't have to worry about proving this statement for prime numbers. So since my theorem applies only to composite numbers, I can just assume that k plus 1 is composite and then try to argue my case from there. So if we suppose that k plus 1 is composite, then by definition, we have k plus 1 equals a times b for some choice of a and b in n, with the property that 1 is less than or equal, or less than, strictly less than, both a and b, and both a and b are also strictly less than k plus 1. Okay, so now, what do I know? Well, since a and b are both strictly less than k plus 1, they must be less than or equal to k, and that means that the inductive hypothesis applies. So here, the inductive hypothesis applies to both a and b, since each is no larger than k. And my inductive hypothesis tells me something about natural numbers that are no larger than k. I know that if they're composite, then they are factorizable. So if a and b are both prime, so that's a case, I'm doing a little mini proof by cases here, then I'm done. This would be my prime factorization if both a and b are prime. If not, then the composite factors can be factored into primes. So in other words, I can factor A and then I can factor B, or if only one of them is factorizable, I can factor that one. And the result either way will be a product of primes that give me k plus 1. So this would give me a prime factorization for k plus 1 as was to be shown. So this is a very fundamental and important theorem in arithmetic that we're now able to prove using our techniques of strong unbounded induction. The reason we had to use strong unbounded induction here is that if we look at A and B, which we got by applying the idea that k plus 1 is composite, we knew there must be such an A and B. We had to go back. So A and B are smaller numbers, which means that we had to go backwards in our chain of propositions. But we didn't know how far back. We didn't know whether it would be enough to go back 3 steps to say something about A and B, or 5 steps, or 2,000 steps. There's no way to know in general. And so because we don't know in general, we just assumed that our statement was true of everything up to the point we were at, up to the point of k, in order to prove our statement for k plus 1. So that's where the unboundedness of strong unbounded induction helped us out.